lesson is on solving linear inequalities. Suppose I want to solve the linear inequality y is greater than or equal to 2x minus 3. Then what I'd be trying to do is find points that satisfy this inequality. For example, if we look at the ordered pair -2, 3, and substitute x with -2 and y with 3, our inequality would read 3 is greater than or equal to 2 times -2 minus 3. In other words, 3 is greater than or equal to -4 minus 3. 3 is greater than or equal to -7. Because 3 is greater than -7, this point satisfies the inequality, so it would be considered a solution. If we look at the ordered pair 1, 2, and replace x with 1 and y with 2, our linear inequality would become 2 is greater than or equal to 2 times 1 minus 3. In other words, 2 is greater than or equal to 2 minus 3. 2 is greater than or equal to -1. And since 2 is greater than -1, this point satisfies the inequality and it would be considered a solution. If we look at the ordered pair 0, -3 and substitute it into the inequality, we would get -3 is greater than or equal to 2 times 0 minus 3. -3 is greater than or equal to 0 minus 3. So -3 is greater than or equal to -3. Since -3 equals -3, this would be considered a solution to the inequality. And so I've shown you 3 solutions, and it turns out that there would be an infinite number of solutions to this inequality. Now, it would be impossible to write an infinite number of ordered pairs down. So what we do instead to solve a linear inequality is we graph it. There are going to be 3 steps to follow when graphing a linear inequality, and the first step is to graph the boundary line. In this example, the boundary line would be the equation y is equal to 2x minus 3. You might recognize that as being in slope-intercept form, y equals mx plus b. So it's telling us that the slope is 2, or the fraction 2 over 1, and the y-intercept is -3. So we begin by placing the y-intercept on the y-axis at -3. There's the first point on our line. And then the slope of 2 over 1 tells us to go up 2 and right 1 to find the next point. And we can continue that pattern of going up 2 and right 1 to find more and more points. So I'm kind of outlining where I need to draw the line. But the next step is to decide whether to make the boundary line dashed or solid. And what's going to determine that is the inequality. When you have an equals, it's saying that points on the line itself satisfy the inequality. So to show that you want to include points on the boundary line, you're going to make it a solid line. So it's going to be solid whenever it's greater than or equal to or less than or equal to. Now when it's just strictly greater than or strictly less than, when you don't have the equals, then that means points on the line are not going to satisfy the inequality. So to show that you don't want to use the line, you make it a dashed line. So because we have the equals, we're going to make our line solid. So the next step is to decide whether to shade above or below the line, and we're going to use a test point to make that decision. You might recall from my earlier work, I showed that this point satisfies the inequality and this point satisfies the inequality. So both of those could serve as test points. Since they make the inequality true, we want to shade the side of the line that contains these test points. So we would be shading what would be considered above the line. All of these points that I'm shading in have y's that are greater than the line. Now, if I didn't do that earlier work, a good point to use as a test point if it doesn't lie on the boundary line is 0, 0. Because it would be real easy to plug zeros into this inequality. We would get 0 is greater than or equal to 2 times 0 minus 3. And since 0 is greater than 0 minus 3, since 0 is greater than or equal to -3, you can see that this point makes the inequality true. So when the test point works, you want to shade the side of the line that contains the test point. If the test point does not make the inequality work, you want to shade the side of the line that does not contain the test point. Okay, so what our graph is showing us is that any point in this shaded area, this point, and this point, and this point. Any point in our shaded area is a solution. And furthermore, because the line is solid, any point on the line would satisfy the inequality. So we're showing an infinite number of solutions when we make this graph, and our solution is complete.